Welcome to our electric circuit analysis series. Today we're going to talk about charge and current. Charge is an electrical property of atomic particles. Protons have a positive charge and electrons have a negative charge. The symbol for charge is Q. Charge is measured in coulombs. Therefore, 1 coulomb is the basic unit of charge. The symbol for coulomb is C. The charge contained in a single electron is negative 1.602 times 10 to the power of negative 19 coulombs, while 1 coulomb contains 6.24 times 10 to the power of 18 electrons. This means that in a single electron there is a very tiny amount of charge. We can rewrite this as negative 0.0000000000000000. That's actually 18 zeros followed by 1602 coulombs of charge. That is a very small amount of charge. On the other hand, in 1 unit of charge, meaning 1 coulomb, there are very many electrons. We can rewrite this as 624 followed by 16 zeros. 0.0000000000000000. And this is how many electrons there are in 1 coulomb, which is a very large quantity of electrons. The formula for charge is Q equals N times E. N stands for the number of electrons, and E stands for the electronic charge per electron, which again is negative 1.602 times 10 to the power of negative 19C. The electronic charge contained in a single proton is the same magnitude as that of an electron, but with a positive value. So positive 1.602 times 10 to the power of negative 19 coulombs. And we can find the amount of charge contained in any number of protons using this formula, N times P. So now let's talk about current. What creates electric current in an electric circuit? Here we have a very basic circuit containing a voltage source and a resistor. Current is created when positive charges move in one direction while negative charges move in the opposite direction. This motion of positive and negative charges is what creates electric current. The conventional direction of a current is the flow from the positive terminal of a power source to the negative terminal of the power source. This is the same direction that positive charges flow. Electrons, on the other hand, flow from the negative terminal to the positive terminal of a power source, so they flow in the exact opposite direction of the flow of positive charges. So when we talk about current, we will actually be referring to the flow of positive charges. This is known, again, as the conventional direction of current flow, the flow of charges from the positive terminal to the negative terminal of a power source. Current is a time rate of change of charge. The symbol for current is I. It is equal to the change of charge per unit time. Substituting Q with NE from our earlier formula gives us dN over dt times E, since E is a constant number. So we can just pull it out in front of the derivative of the number of electrons with respect to time. Current is measured in amperes. The symbol for amperes, also called amps, is A. Therefore, 1 ampere, or 1 amp, is equivalent to 1 coulomb per second. Current is really the amount of charge that flows through a particular point in a circuit. So if we take any point in a circuit, then the current is equal to the amount of charge that passes through that point per second. Now, if we take this formula for current, we can derive the formula for charge, which is equal to the integral of the current multiplied by dt, which is the change in time measured in seconds, integrated from some initial time to some final time. So we can find the amount of charge that has flowed through some particular point of a circuit by integrating the current that has flowed through that point over a certain period of time. Notice that this formula is comprised of a definite integral, denoting a specific initial time as well as a specific final time. However, if we are not given the specific time period, then we can use this formula, which includes an indefinite integral of the current, as well as an initial charge, which we can determine by using a given initial condition. For the purposes of this tutorial, we will be referring to current as direct current, also known as DC current, which is current that flows only in one direction. Alternating current, on the other hand, flows in both directions and changes direction with respect to time. We will cover AC current later on in this electrical circuit analysis series. This example asks for how much charge is present in 8,400 electrons. So we can use this formula right here, Q equals N times E, since we have the number of electrons and we already know the electronic charge per electron. The number of electrons is 8,400. The electronic charge per electron is negative 1.602 times 10 to the power of negative 19 coulombs. So here all we do is just multiply 8,400 times negative 1.602 times 10 to the power of negative 19. And we get this for an answer, negative 1.346 times 10 to the power of negative 15 coulombs. And this is our final answer. In this example, we are asked for how much charge is present in 5 billion protons. Again, we can use the similar formula. However, this time, we're going to use NP instead of NE, obviously, because we're going to be using protons instead of electrons. So N here is going to be 5 billion. So 9 zeros. Is also equivalent to 5 times 10 to the power of 9. The electronic charge per electron is 1.602 times 10 to the power of negative 19. In a similar way, we multiply 5 billion times 1.602 times 10 to the power of negative 19. And here we get 8.01 times 10 to the power of negative 10 coulombs. And this is our final answer. Let's look at this example here. If the charge flowing through an element is given by Q of t equals 3 times e to the power of negative t minus 5 times e to the power of negative 2t, and the unit of this is in nanocoulombs, what is the current flowing through that element? So let's write down our given here for the equation of charge. We can use this formula for current. Finding the derivative of Q of t with respect to time. So we replace Q with its equation. Break up this derivative. Into two parts. And let's solve for this first part here. Let's bring the constant out to the front. we get 3 times e to the power of negative t. And because of chain rule, we find the derivative of negative t. And we get negative 3 to the power of negative t times 1. And we get that. And so for this second part right here, we get negative 5 out front. Again, because of chain rule, we find the derivative of negative 2t. And we get this answer here. Now we put those together to get our final answer, negative 3 times e to the power of negative t plus 10 times e to the power of negative 2t. And this will be in nanoamps, since we're given nanocoulombs here. Always make sure we get the right units. And that's our final answer. So now with this example, we are asked if the current flowing through an element is given by I of t is equal to 3 amps, and we're also given an initial condition, Q of 0 equals 1 coulomb. The question is, what is the charge flowing through that element? Let's write down what we're given. We have the current I of t, which is 3 amps, and we have Q of 0, which is 1 coulomb. This is known as an initial condition. We can use this formula to find the amount of charge. Q of t equals I times dt, the integral of I times dt, plus Q of t0. Since we're not given a specific time period, we're using this formula with the indefinite integral. And so let's solve for this first. That's going to be the integral of 3, as we can see here, times dt. You can pull out the constant 3. We know that 1 is equivalent to 1 times t to the power of 0. And so we can replace this with 3 times the integral of t to the power of 0 dt. And we get 3 times t to the power of 1 over 1, which is equivalent to 3t. And that's our Q of t. But remember, this is an indefinite integral. And so there's going to be some constant left over. This is going to be our initial charge. And this is not equal to the initial condition. However, we do use the initial condition to find our initial charge. And here's how we're going to do that. We have our initial condition of Q of 0 being equal to 1. Q of 0, plugging 0 into this equation, we get 3 times 0 plus C, which is also equal to 1. Therefore, C is equal to 1. And now we have our complete equation, 3t plus 1. And again, let's not forget our unit of coulombs. And this is our final answer. Note that this value is a positive value because we're using the conventional direction of current, which follows the direction or the flow of positive charges. Now let's look at a similar example. If the current flowing through an element is given by I of t is equal to 20 times the cosine of 10t plus pi over 6, and our initial condition is Q of 0 as 2 microcoulombs, the question is, what is the charge flowing through that element? And again, we'll use this formula right here. Q of t equal to the integral of it dt plus Q of t0. Again, this is the initial charge, which will be found or determined using the given initial condition of Q of 0 equals 2 microcoulombs. So let's solve this. Let's take on this part first. It's going to be the integral of 20 cosine 10t plus pi over 6 dt. We're going to use U substitution. So basically, let's say U is equal to 10t plus pi over 6 du equals to 10 times dt. Therefore, du over 10 is equal to dt. And so we'll replace dt here. Well, we'll replace 10t plus pi over 6 with u, and then we'll replace dt with du over 10. And so let's bring out the constants. Here we have 20, and here we have 1 over 10. So we'll have 20 over 10 times the integral of the cosine of u du. And so we have 2 times the sine of u. And we'll plug back in the value, the original value of u, which is 10t plus pi over 6. And we get 2 times sine of 10t plus pi over 6. Again, because this is an indefinite integral, we have some constant left over. So let's use our initial condition right here. And let's plug in 0 into this equation. So we have Q of 0 is equal to 2 sine 10 times 0 plus pi over 6 plus c. And q of 0 is equal to 2. Therefore, 2 is equal to 2 sine of pi over 6, since this cancels out to be 0, plus some constant. And we know that sine of pi over 6 is equivalent to 1 over 2. And so we have 2 equals 2 times 1/2 plus c. Therefore, c is equal to 1. And so we get our final answer. Q of t is equivalent to 2 times sine of 10t plus pi over 6 plus 1. And of course, we have our unit here, since we're using microamps and microcoulombs. We'll have our unit as microcoulombs. And here's our final answer. For this example, we are given a graph that shows the amount of charge that flows through a wire. And we need to draw the graph for the corresponding current. So here we have an interval from 0 to 2. We also have an integral from 2 to 6, and our last interval from 6 to 8. So let's determine the different currents that are flowing through that wire in these 3 intervals. So let's start with when time is between 0 and 2. And we'll use this formula here to find the current. I equals the derivative of Q with respect to time. So really all this means is that this numerator is equivalent to the change in Q over our denominator will be the change in time. So here, between 0 and 2, we start at 0 on the y-axis and we end up at 50. Therefore, the overall change in Q is 50. And the overall change in time, which is the x-axis here, we move from 0 to 2, and so we have 2 units here. Notice that this value right here is the slope of this equation, because that's what a derivative is. The derivative is the slope of any equation, the slope of any line. Therefore, I is equal to 25 amps on this interval. Now let's look at when time is between 2 and 6. We'll use the same formula. And we see here, between 2 and 6, we start at positive 50, and then we end up at negative 50. And so we have a total change of negative 100 units on the y-axis. Therefore, we had negative 100 at the top here for the change in Q. And for the bottom, we go from 2 seconds to 6 seconds. Therefore, the change in time is going to be 6 minus 2, which is 4 seconds right here. And so between 2 seconds and 6 seconds, current is equivalent to negative 25 amps. Now in our last interval here, between 6 seconds and 8 seconds, again, we'll use the same formula for all of these. Our change in Q, you start at -50, end up at 0, so there's a total change of +50. And our change in time, since we start at 6 and end up at 8, our change in time is going to be 8 minus 6, which is 2 seconds. And so between 6 and 8 seconds, the amount of current flowing through that wire is going to be 25 amps. Okay? And so now we can draw the graph for the current. So between 0 and 2 seconds, we have current at 25 amps. And between 2 and 6 seconds, we have current at -25. And then between 6 seconds and 8 seconds, we go back to current being 25 amps right here. And so we can connect these equations. Okay. And here we have our answer. Now, for our last example, we are given a graph, this time of the current, with respect to time. This is the amount of current that has flowed through an element, and we're asked for how much charge has passed through that element at these 3 given times: 1 second, 3 seconds, and 5 seconds. Okay, so there's actually 2 main methods of solving this kind of problem. The first method, we're going to call it the area method. And basically, we're solving for charge. We know that charge is the integral of the current. Therefore, if we're solving for the integral, we know that we're just solving for the area underneath the graph, right? Between 0 and 1, we're going to solve for this area right here. So let's do that first. And so when t is equal to 1 second, Q is going to be equivalent to this area of this rectangle with a length of 10 and a width of 1. So it's just 10 times 1. Which gives us 10 coulombs of charge that has flowed through this element between a time period of 0 and 1 second. Now let's solve for when our time is at 3 seconds. This one's a little bit trickier. We're going to solve for this area right here. This whole area, including this initial area that we've already solved for. So since we've already solved for this initial area between 0 and 1, we're just going to find this area between 1 and 3. And we're going to break this up into a few different areas here. We have an area of a rectangle here. An area of a triangle. We have another area here of a rectangle. Similarly, we have the same rectangle here. And so what we're going to do, since we already know what the area is between 0 and 1, we'll just copy that over. That's 10. Plus, let's solve first for the area of this triangle. We know that an area of a triangle can be found through this equation, height times the base over 2. And so the height of this is going to be 5 units on the y-axis, and it's going to be 1 unit for the base. And so that's going to be 5 times 1 over 2. And we have to add the area of this rectangle, which has a length of 5 and a width of 1. So we'll add that. Okay? And this is going to be our total area for this interval. And now let's get the area here, which is going to be easy. It's going to be the same as this rectangle here, which is just 5 times 1. And so we get 10 plus 7.5 plus 5. And so we get our total answer of 22.5 coulombs. So far, we've got our answers for when time is at 1 second and when time is at 3 seconds. Now let's solve for when time is at 5 seconds. Let's make this a little bit smaller, make some room. Okay, so here, charge is equivalent to, well, we already found this whole area between 0 and 3. So we'll just plug that in. And then we'll find the area between 3 and 5, which is going to be this rectangle, this interval between 3 and 4 seconds, and then this triangle between 4 and 5 seconds. So firstly, let's plug in our value here, 22.5. For the time interval between 0 and 3 seconds. And then between 3 and 4 seconds, we have this familiar rectangle here with a unit length of 5 and a width of 1. So it's going to be 5 times 1. Plus we have another triangle here with the same measurements as this one actually. So it's going to be 5 times 1 over 2. And so we have a total of 30 coulombs of charge between 0 and 5 seconds of time. So now we've solved this using our area method. Let's try our second method of actually using our calculus formula here. So we'll be referring to this formula here. The first thing we're going to do is we're going to find the piecewise function for I. And we're going to do that using the different intervals. From 0 to 1, from 1 to 2, from 2 to 4, and from 4 to 5. So from 0 to 1, we have that I of t is equivalent to this line. Let's refer to this equation. We need to find the slope and the y-intercept for each of these equations that make up the whole piecewise function for I. Again, between 0 and 1, we have a slope of 0, essentially. This is just a line here. So that's just 0 times t, plus our y-intercept is clearly at 10 here. Therefore, I of t is equal to 10 amps for this interval. And so, between the interval of 1 and 2 seconds, we have that I of t is equivalent to, let's find this slope here. We're going down by 5 units, -5, and then we're going to the right by 1 unit. And so we have -5 over 1 times t plus, we have some constant here, c sub 1, for where this slope intercepts the y-axis, somewhere here. Now we can find this value of c sub 1 by just plugging in let's plug in 1 to I. We're going to use some value of I within this interval now. So let's use I at 1 second. At 1 second, we have I at the value of 10, right? Right before it starts going down to 2. We have a value of 10 for I. And so I of 1 is going to be equivalent to 10. And plugging in 1 into I there, into our equation here for I, we're going to have -5 times 1 plus c sub 1. Therefore, c sub 1 is equivalent to 15. And so we have I of t is equal to -5 t plus 15 amps. So now let's find I for the interval between 2 and 4 seconds. Between 2 and 4 seconds, we have a straight horizontal line here with no slope. And we can see clearly that it would hit 5 here at the y-intercept. Therefore, this equation is going to be 0 times t plus 5. Therefore, I of t is just 5 amps between 2 and 4 seconds. And for our last interval here, when time is between 4 and 5 seconds, we see that, again, we have a negative slope going down 5 units, right, from 5 to 0, and then going to the right 1 unit. And so again, we have a slope of -5 plus some constant c sub 2 for where this would hit the y-intercept here. Again, we're going to use a value between this interval. So let's use I of 4. We have a clear value here for I of 4 is equal to 5, right? And so let's plug in 4 into this equation. And so we have -5 times 4 plus c sub 2. We know that I of 4 is a value of 5, as shown here. And so 5 is equivalent to -20 plus c sub 2. Therefore, c sub 2 is equivalent to 25. And so we have I of t as being negative 5t plus 25 amps between 4 and 5 seconds. So now let's put that all together. Once we put that all together, we get our piecewise function for I, which between 0 and 1 is 10 amps. Between 1 and 2, we've got negative 5t plus 15 amps. And between 2 and 4, we have 5 amps. And between 4 and 5, we have negative 5t plus 25 amps. And this is our piecewise function. So now let's go back to this formula to find charge using the integral of I with these specific initial and final time values. And this is going to be super easy and should give us the exact same answers as our first method did. So when t is equal to 1 second, we have that q is equivalent to the integral from 0 to 1 second of 10 dt. That's the equation we have for this interval. And so this is equal to 10t evaluated from 0 to 1. Therefore, q, or charge, is equal to 10 coulombs between between 0 and 1 second. That's the exact same answer we got for our first method using area. Now, when t is at 3 seconds, we're going to find q by finding the integral from 0 to 3 seconds of I of dt. And what we're going to do here is we're going to break up this integral into 3 different integrals, since we have 3 different intervals here: 0 to 1, 1 to 2, and then 2 to 3. Okay? And so we get this first part from 0 to 1 of I of dt, plus the second part from 1 to 2 seconds of I dt, and lastly, from 2 to 3 seconds, our integral of the current here. And this is going to be equal to 0 to 1 of 10 dt plus 1 to 2. Plugging in our equations now. Oh, I'm sorry, this has a t right here. Plus 15 dt plus our integral from 2 to 3 of 5 dt. We're just going to follow this 5 between 2 and 4, right? Except this is just going to be from 2 to 3, obviously. Shares the same equation. And so I'll let you go ahead and solve for the value of these integrals. And in the end, we get 10 plus 7.5 plus 5. Therefore, we have a value of 22.5 coulombs total charge from 0 to 3 seconds. Now let's look at our last interval here. From 5 seconds, our last time. And we'll just do something very similar to what we've been doing. Integral from 0 to 1 of the current plus 1 to 2 of the current plus integral from 2 to 4 of the current. And lastly, from 4 to 5 seconds. And I'll just rewrite it all out so you can get a clear picture of what's going on. And then our last interval here from 4 to 5, negative 5t plus 25 dt. These are just, again, the equations in our different intervals here in our piecewise function. Again, I'll let you guys solve for these integrals part by part. And in the end, we get a total value of 30 coulombs. Total charge from 0 to 5 seconds. And that's our final answer using our second method of calculus. This lecture is included in Unit 1 of our electric circuit analysis series, where we cover basic concepts including charge and current, voltage, and power and energy. The formula sheet for this entire unit is available for purchase at payhip.com/EngineerPeer. Right now, all our formula sheets are on sale for 50% off.